start now. So thank you, everybody. So for good morning to welcome to my PhD defense, and which is supervised by Anna Hopima and Peter Van Beek. And thanks a lot to all the jury members for examining my manuscript of my PhD thesis. So today I'm going to present you my PhD work about Cenozoic topography evolution in Southeast Tibet, focus on the Mekong and the Yalong rivers. So as we all know, the continuous India-Asia collision since it's around 50 million years plays a principal role during the construction of the high and vast Tibetan plateau, which has an average elevation of 5,000 meters and a surface of more than 2 million square kilometers. And the complex and long-term tectonic has largely uplifted and deformed the whole plateau. At the same time, the climatic evolution, for example, especially like the emplacement of the Asian monsoon and a strong orographic effects on precipitation on the plateau, has largely worked together to sculpture the geomorphology of the plateau. So the Tibetan plateau has always been one of the most interesting places to study the interaction between tectonics, climate, and erosion, and how they influence the topography evolution together. So this interaction in different ways across the whole plateau results in very contrasting topography. If we look at the whole plateau from the southeast direction, we clearly observed very strong, steep topographic steps across the Himalaya and the Longmen ranges, as we can see on this sweat profile. But in contrast, the plateau interior is relatively flat. And very interestingly, our study zone, the Southeast Tibet, shows a very gradually decreasing topographic gradient over a long distance of 2,000 kilometers. So this remarkable flatness of the plateau interior, which is colored in blue here on this slope angle map, which is in contrast with the steep margins marked by yellow here. And the low relief surfaces of the plateau interior roughly overlaps the extensive endorheic zone, which is delimited by this white line. But one thing to note is that the vast distribution of the middle Miocene lacustrine deposit marked in light blue shows that the endorheic zone was much larger and vaster farther to the east of the Tibetan plateau before being captured and drained by those large rivers to the southeast. Those large rivers, including the Yellow, Dadu, and Yalong rivers to the east, and also the Salween, Mekong, and Yangtze River, which flows very parallelly and very closely to each other to the southeast in the Three Rivers region. So the earthquake focal mechanism showed that the present-day deformation and the tectonic region of the Tibetan plateau is dominated by the compression marked in red here along the plateau margins, like the Himalaya and the Longmen thrust belt. And it's also dominated by the extension marked in green here in the central part and some of the southern part, and by the large-scale strike slip deformation, many in the southeast Tibet, in the central and the western part. So this large-scale strike slip deformation of southeast Tibet could be better illustrated by the present-day GPS velocity field in a Tibet fixed reference. As we can see, it reveals a large-scale crust motion in horizontal direction along the Xiong and Jiali faults, one of the most active faults of Tibet in today. It clearly shows southeast extrusion of the southeast Tibet, and as well as a clockwise rotation of it around the eastern Himalayas and axis. So if we take a look at the topography of southeast Tibet, it is dominated by a coexistence of the low relief surfaces at high elevation, marked by blue here, like the Daochen Massif at 4,500 meters high, as we can see on this photo, and also characterized by the deeply incising river marked in yellow here, as we can see on this photo of the Yalong River Gorge with a depth of 2,000 meters. So the low temperature thermochronology, a method that I will present to you a little bit later, show that we have very old ages marked in green here on the low relief surfaces, which means there has been no exhumation or very little erosion since at least the India-Asia collision. And we also see very strong incisions in the river valleys across the whole Tibet plateau, the Southeast Tibet, like in the Yalong River, the Salween, and the Mekong rivers, or even in Yangtze River here. So during the past 2 decades, there has been 2 principal models trying to explain the mechanism of generating such peculiar topography of the Southeast Tibet. The first one comes from the Clark and Tell 2006, sorry. And they proposed that the surface uplift of the Southeast Tibet comes from a regional lower crust channel flow and from a flat lowland, and then they have been dissected by the regressive fluvial erosion. In the model, they predict almost no erosion on the low relief surfaces at high elevation. And also the rock uplift is roughly equal to the surface uplift. And this regional low crust flow, channel flow comes from the partial melting of the thickened crust of the Tibetan interior, and the viscous materials flow to the southeast and to the northeast under the gravitational gradients. And this crust flow uplift the lowland or the foreland without major upper crust deformation. So the second model comes from the Luzon et al. 2008, which proposed the surface of the Southeast Tibet was majorly uplifted by the large-scale folding and thrusting. And then they have been dissected by the coeval fluvial erosion. And they observed in their model not very strong, but considerable erosion on the low relief surfaces at high elevation, as we can see here. And evidently, the rock uplift is larger than the surface uplift. So this uplift pattern comes from the model of comes from the rigid block extrusion model of Taponia, which predicts localized deformation along the major tectonic structures here, and also a southeastward extrusion of the Indochina block during the Oligocene. So until now, even though we have so many proposed models, but how was this particular topography of the Southeast Tibet was generated remains highly debated. And we understand from above that understanding the topography evolution is very essential for understanding the plateau growth mechanism. And how can we quantify the exhumation rate and exhumation amount? Also, what kind of role does the uplift, UV incision, and the climate play during the topography evolution, and how they react with each other in a local or regional scale? That's all the questions I would like to answer during my PhD work. So for the first part, I will talk about the topographic growth and the incision of Southeast Tibet, focus on the Mekong River by using low temperature thermochronology and a 3D thermokinematic modeling per cube. And then for the second part, I will talk about the topographic evolution of Southeast Tibet, focus on the Yalong River by using a netscape evolution modeling FastScape. So for the first part, the method that I used is called low temperature thermochronology, which is based on the radioactive decay of the parent elements like the uranium and thorium by generating the daughter elements like the helium and the fission tracks in minerals like apatite and zircon. When those minerals are located in depths over a certain closure temperature, it forms an open system. That means all the produced daughter elements, they will flit away. Nothing is kept in the system. And then once the mineral has been exhumed by passing this closure temperature, the system will be totally closed by retaining everything inside. The daughter elements. So, sorry for the color. So different minerals and different melasters, they have different culture temperatures. So in my study, I principally used the apatite helium and the fission tracks and the zircon helium. If the minerals, they continues to be uplifted onto the surface, the duration is defined as the cooling age, which could be calculated by quantifying the quantity of the helium and the fission tracks in the minerals in the closed system. And if we plot these cooling ages against the elevation of all the samples from one vertical transect, the slope here will give us the exhumation rate. And like in the case of the vertical exhumation, of course, this exhumation could be related to pure river incision or fault activities. With the youngest ages always located near the river bottom or near the active faults. So with all those thermochronological data, it could help us to reconstruct the crustal thermal history. So in such a model with a specific thermal structure and a topography, we can test the different scenarios of rock cooling, which could be related to a regional block exhumation, or a fault slip movement, or to a river incision from an initial plateau. And the model allows us to inverse and constrain the different parameters, such as the exhumation rate, exhumation timing, the fault slip rate, and the geometry of the fault defined by this white spot here, or the exhumation time. I said that, okay. So, sorry. It allows to inverse the parameters by comparing the predicted ages with the observed ones, and the calculated misfit will be plotted in different colors according to the values of the misfit. And this yellow star will give us the best parameters that we are looking for. This yellow star stands for the minimum misfit to us, of course. So let's start it. In the west part of the Tibetan, Southeast Tibet, the Salween, Mekong, and Yangtze flow parallelly and very close to each other to the southeast. And they all have very deep valleys, like we can see on this photo of the Mekong River. They have like 3,000 meters of depth for the valley. So in the core area of the three river regions here, across the Mekong River, the Grenoble Massif to the west side shows a rugged topography at high elevation, which we can observe on the Swartz profile here. And it's also demonstrated by the strong local relief marked in red here. While in contrast to the other side of the Mekong River, the Baimei here, which is considered as part of the low relief surfaces marked in blue here and here. It has a much flatter and lower topography. So, and the existing thermochronological data from the Grenoble Massif at a low elevation, they're all younger than 10 million years, marked in red here, even including the zircon helium ages, which is interpreted as a very fast exhumation, which is caused by a local reactivation of the north-south local reactivation of the source and north thrust between the dextral, Paolin, and the Zhongdian faults. While all the ages from the Baimei Shishan is really, really old, as marked by the dark color here, and they only show a very slow exhumation. So this area with such a strong contrast in terms of the topography and the thermochronological data could be an ideal region for us to study the different roles of the regional or local uplift, or the river incisions during the exhumation history of the Three Rivers region. I will do that with the PyCube. So let's take a look first at the Baimei Shishan to the east side, which the old ages marked in blue here. So first of all, I tested a steady state scenario with all the three thermochronometers in in a steady state scenario, which means that they have an unchanging topography. Results show that the whole age patterns are quite well reproduced, marked in red here, except all those young appetite helium and the fishing tracks very close to the river valley. And this model gives us a very strong exhumation since 7 million years with a rate of 0.0 km per million year after long and slow exhumation phase. And next, in order to decipher the role of the Mekong River incision during the exhumation of the Bamei-Shishan, we implemented an initial plateau of 0.5 kilometer, which evolves into the modern present topography. The results show that the result is plotted in gray here, and it shows that only the very, very young ages of apatite helium can be reproduced here. And it has to be close to the river valley too. And all the apatite fission tracks ages or apatite helium ages at high elevation, they're really old. And the zircon helium ages, they're homogeneously old. I mean, even they are in the range of all the blue observed ages, you know, but they are too homogeneous. So they didn't work. So next, by coupling such a river incision and a local uplift in a plateau scenario, we can better constrain the neogen history of the Bamei-Shishan, which means we have a better prediction ages for all the young ages, marked in orange here. And this scenario gives us a very fast exhumation since 10 million years at a rate of 0.25 kilometer per million year, and also a river incision since 10 million years with a lower misfit, with a quite low misfit. So a 3D view will show us better that a combination of the river incision and also a rock uplift since 10 million years is necessary to reproduce all the age distribution for the Bamei-Shishan massif and to better constrain the neogen history of here. And all the parameters are quite well constrained. I would say even very good. And the Mekong River incision from this flat model scenario is only 1 kilometer, only accounting for 30% of the total dimension. So now let's move to the other side of the Mekong River. So the coverage with the very young ages who are marked in blue here. So first of all, we also tested a steady state scenario with the unchanging topography. And also we tested a tectonic scenario with one segment thrust, which is free to be inversed by the per cube. The result all show that the age prediction is quite inconsistent with the observed one. So they don't work either. So if I inverse a 2-segment thrust in the same tectonic scenario for the coverage massif, we see the age quite good. The age are quite good, and we even have a perfect slope break, as we can observe on the yellow, the observed ages marked in blue here. And the inverse fault dips to the west side at an angle of 65 degrees and until a depth of 8 kilometers, and then it flattens like here. So in order to be compatible with the Bamei-Shishan to the other side, we also included the plateau, river incision from an initial plateau in this scenario. This scenario has a similar prediction of ages, but it gives us a very strong exhumation since 10 million years at a rate of 0.5 kilometer per million year, before an acceleration to 2 kilometer per million year since 2 million years with a slightly lower misfit. And the 3D visualization show that a variation of the exhumation rate above the Mekong thrust is necessary to reproduce all the age distributions in distance with respect to the thrust trace in the surface. And for this scenario, the Mekong River incision is of 2 kilometers, accounting for 20% of the total exhumation, which is similar and compatible with the Bamei-Shishan massif to the other side. So to conclude this small part, our result showed that the strong and fast exhumation in the coverable massif is principally dominated by a local thrust in a restraining band between the pollen and the Zhongjiang fault since at least 10 million years. And the slow and much less important exhumation in Baimei-Shenshan here is more controlled by a regional uplift. And for both massifs, the river incision of the Mekong since 10 million years accounts only for 25% to 30% of the total exhumation, as we can see by blue here. And we also observe a remarkable removal of the overburden of 2.5 kilometers since 10 million years on the Baimei-Shenshan massif. So these low relief surfaces of the Baimei-Shenshan massif, due to the strong erosion, is more, this is thought to be related to the, this strong erosion is thought to be related to the enhanced mousson or precipitation, or the basal soil-like glacial erosion since at least 2 million years. So the low relief surfaces of the Baimei-Shenshan, due to the strong erosion, is more consistent with the model proposed by the Luzon until 2008. So in the end, in the core area of the Three Rivers region, we succeeded to observe, investigate, and determine the different roles of the regional and local uplift, and also the river incision in the contrasting exhumation and the topography evolution for those two massifs across the Mekong River. But that's quite cool. So like here is a 3D view of the two massifs, which shows very different topography. You can see here is high and rugged. On the other side is less high and more flat. And we can observe a lot of like thrust in the north-south direction and between the pollen and the Zhongjiang faults. And the pity is we only have very recent histories since 10 million years for the coverable, for the high coverable. So in 2019, we did a field mission at the higher elevation of the glacial valley of the coverable massif, trying to cover a longer tectonic history. And as we have seen, the uplift of the coverable is more related to the thrust in the north-south direction, which could be traced in this regional map to the north and to the south too. So those large-scale distribution of the thrust and the narrow spaces between the large rivers in the Three Rivers region has been always used to show a very strong southwest compression due to the continuous indenting India plates, which is very nicely shown by these highly compressed ellipses. Indeed, some recent thermochronological data from the north near the Zhougong show that a reactivation of the Longmotor Shuanghu Shichu as a local thrust during the 40 to 20 million years, and also very strong river incision along the Salween to the south. All those has been thought to be related to the strong compression of the Indian plate to the northeast. And at a regional scale, this continuous indentation has been also suggested to cause the southeastward extrusion of the Indo-China block along the large-scale Ailo-Shan-Red River shear zone to the along here, and the Gaoli-Gong shear zone here, with the strong shearing along them and then almost no deformation inside the block. And it happens all during the Oligocene. So our new data from the cover table at high elevation in the middle could help us to enrich our understanding of the tectonic evolution of the whole Southeast Tibet. And here is a 3D view of the location of our samples and the age distributions on this photo. And all our new ages could reach up to 32 million years, more or less. And we observe a very strong dispersion of the apatite, helium, and the fishing tracks at high elevation marked in blue here. And we also used the cube to model all those new ages by adopting the same geometry of the thrust from the first part. And the result showed that the age at the velocity distribution above the thrust is still very necessary to reproduce all the ages marked in red here, and the H is quite nicely reproduced, except all the dispersion of the AHE and the appetite efficiency, which normally we cannot do that with the PQ. So, okay, let's forget about it. So this model gives us a very fast excitation phase since 32 million years with a rate of 1.5 kilometer per minute year until 50 million years, and slow down a little bit, and then it accelerates to another very fast excitation rate since 2 million years at the rate of 1.8 kilometer per minute year. And that's the result for the modeling. If we take a look at a regional scale, the young ages and the fast exhumation marked in red, marked in blue here from our coverage massif is quite inconsistent with the data, the reported data from the Zhokong to the north marked in red here, and from the southern. They're all younger than 36 million years, and they show very strong exhumation, and they all located to the west of the Longmotor Shuanghu suture marked in purple here. And also in this region, as we can see, we observe extensive excess of elevation to 5,000 meters, marked in blue here. So if we go to the other side of the Longmotor Shuanghu suture, away from the suture, we'll observe much older ages, marked in by the open symbols here, and less exhumation. And we see almost nothing, no exhumation on the Daocheng massif. So this Longmotor Shuanghu suture must represent a techno topographic boundary which separates the regions here who experienced a very strong compression due to the indentation of the Indian plate, as illustrated by the highly compressed ellipse here, marked in CM. From those regions who experienced less compression, marked by this less compressed ellipse here, and nothing away from it. On the Daocheng surface is a circle, no compression. So if I need to synthesize the tectonic evolution of the whole Southeast Tibet, we can see that the strong southwest, the late Eocene to middle Miocene compression has largely uplifted the Kawa-Zhibu and the neighbor region marked in blue here to the west of the Longmotor Shuanghu suture, and we see no deformation to the east. And this compression, strong compression, is contemporaneous to the southeastward extrusion of the rigid Indo-China block, with the most strong deformation concentrated along the large-scale shear zone, and almost no deformations inside the rigid block. And since 50 to 10 million years, the region of in the southeast Tibet, in the north of the Indo-China, as we can see here, succeeded to be extruded to the southeast between the Jiali and the Red River and the Xianshui strike slip fault systems. And the Kawa-Zhibu has continued to be locally uplifted in a restraining band. And the Kawa-Zhibu has witnessed a transition of the block extrusion from the south to the north. So until now, the first part with the low temperature thermochronology has made us better understand how the different role of the rock uplift, the incision during the exhumation. And then, but in this part, we see that the PQ that we used only stimulated the river incision by changing the topography, and it doesn't resolve the erosion processes. So we need another tool, Fastscape, in our second part, which really resolve the fluvial erosion and the landscape evolution in a physical way. And in this part, I will use the Yellow River catchment as an example. So on this topographic map of the Southeast Tibet, contrasting colors has been chosen on purpose to show the coexistence of the largely deep incising river and the low relief surfaces at high elevation here, as we have seen on those photos just right now. And we know that the tectonic and the climate have worked together largely to sculpture the geomorphology of the Southeast Tibet. So to understand that, we have to look into the tectonic history first. So generally, the South Tibet could be divided into two regions. The first one is the Three Rivers region to the west, which is dominated by a southwest compression by generating abundant north-south direction thrust, as we can observe here. To the east, the Great Bend region, which is dominated by a northwest to southeast decompression by generating northeast to southeast large-scale thrust belts. And also we can see this thrust has shifted the river courses to the northeast, as we can see on this photo of the Yalong, the first bend for that, and the first bend of the Yangtze River for this region. So for the first region of Three Rivers region, a recent topography evolution model proposed a propagating uplift, kind of like a wave from the northeast to the southeast, combined by a natural shortening, as we can see here, has successfully produced the coexisting deep incising river and the low relief surfaces in the interflow and upstream area. But one thing to note is that they have used a constant coefficient erosion coefficient and a precipitation in their model. So if we move to the Great Bend region, we observe on this thrust profile a very steep orographic topographic steps over the Muli and Jinghe thrust, which has thought to be largely uplifted all the high topography, and also they have shifted the river courses, as we can better see on these geological maps, to the northeast. So in this region, I would like to modelize the same characteristics of the topography. That means the coexistence of the low relief surfaces and the deep incising large rivers. And I will use the Yalong River catchment as an example too. So the Yalong River drainage, the upstream is characterized by a flat, long incised area, but in the middle stream, we can see there is a deep incised gorges with the low relief surfaces just neglected. And these gorges we can observe the better on this cross section of the river valley, and it's also shown by this thrust profile along the Yalong River. And normally we use the high elevation profile to represent the river profile of the Yalong, and the high values of the KSM, which is related to the high erosion rate, is delimited, is located in the place of the Yalong thrust belt, which means the tectonic activities has dominated the erosion patterns here. So in order to modelize all those characteristics, I used the landscape evolution model FASTSCAPE, which resolves the stream power law, which stimulates the river incision and the topography evolution by solving this physical equation. So the temporal variation of the elevation depends largely on the uplift, the erosion, and the hill slope processes. But the KT, the KF erosion coefficient and the KT hill slope sediment transport coefficient will be fixed in our model. And so in this model which has a very similar geometry to the Yalong River catchment, the most important parameters is the uplift marked in the red and the precipitation marked in blue here. Here is a simple example to show how the landscape evolves through time by regressive fluvial erosion towards the upstream, and it's very efficient and very fast, and it works in a very delicate way. So first of all, I will show some basic parameter studies by using the same models, but during a 50 million years with a moderate uplift of 0.1 marked in red here, to make sure the total surface uplift of the southeast belt will not depart the maximum average elevation of 5,000 meters. And in our model results, any increase of the KF, the erosion coefficient, or the precipitation will completely destroy the constructed high topography, and the river will propagate towards the upstream, and it shifts from a linear structure to a very convex substructure. And we see the high elevation profiles, they are very convex up too. and very different from what we see here. So here we observe a strong competition, or kind of like a trade-off effect between the preserving high in fat surfaces and the strong incision rivers. So we need to keep that in mind, and I will come back to that later in my following models. And then there has been several previous hypotheses who proposed that the river incision has been the dominant role during the topographic evolution of the Southeast Tibet. They proposed enhanced musonal precipitation or drainage capture of the upstream since middle Miocene. So the results of those two scenarios show that the plateau is strongly eroded by the efficient regressive erosion due to the strong musonal precipitation. And this kind of like escapement, retreat, regression of the maximum topography is not observed in the tectonic active Southeast Tibet. So we cannot apply that to our study zone, the Southeast Tibet. So in the following, so based on this and the existing semi-chronological data, we know that the Southeast Tibet, except at least our study zone, has been more or less uplifted recently. So indeed, the existing semi-chronological data show that there's a strong uplift phase since 30 million years along the Julian thrust, or a fast exhumation phase, uplift phase since 50 million years along the Mooley thrust. So we implemented that in our modeling. The results show that the uplift phase since 30 million years cannot reproduce a quite proper river profiles as we can observe along the Yangtze River here. But the phase since 50 million years can give us a quite similar river profiles as we can observe as along the Yangtze River, and the high elevation profile is quite nice too, but we cannot reproduce the distribution of the high KSM values is everywhere. And we don't have any preserved low relief surfaces along the river. So we still continues to work on that. So now we almost have the right uplift parameters for our modeling. But if we remember the competition between the strong precipitation or the weak precipitation, which can who works together for the first parameter study, we understand that we need to investigate into the paleoclimate evaluation, especially the paleo precipitation. So first of all, in the Southeast Tibet, we observe a very strong orographic precipitation effect on reducing the precipitation once we pass elevation of 3,000 meters along the Yalong thrust belt, and the effective precipitation will decrease from 1 meter per year to 0.2 meter per year. And also the offshore sedimentary rotation rate in the epicontinental seas from the East and the South Asia show that there's a strong precipitation since at least the onset of the monsoon, and also a very weak precipitation during 10 to 5 million years. So we incorporate all that in our final model by using a weak precipitation on the high plateau since 10 million years. And also we need a strong water inflow in the uppermost part of our model with a water inflow of 1 meter per year, trying to mimic the potential capture of an indirect zone or the large quantity of the collected water from the large upstream areas in our model. And by combining our strong recent uplift in our final model, our results show that we can quite satisfyingly reproduce the topography of our study zone, which means we have a low relief, not really incised the upstream, and middle stream with the large, deeply incised the river gorges, as we can see on this cross section, positioned by this green line. And as we can also see on the thrust profile along the river, along the Yangtze River. And we also observe low relief surfaces in the interflow spaces. And the high elevation profile show that the river the model of the river is quite nice and proper, and it's very similar to the Yangtze River. And we also have like the highest KSM values concentrated along the thrust belt. So, okay, well, it works quite well. So now we come to the conclusion part. Cool. So in a regional scale, in our Great Banks region, the Yangtze River catchment is delimited by this black line here, and the river flows in the upstream without incision. And then in the middle stream with the really deep gorges with the low relief surfaces, we have heard about that a lot. And then it flows into the foreland, which is very strongly eroded with the low elevation. And it is separated from the middle stream by the Moody thrust, one thrust of the Yangtze thrust belt. And for this catchment, we propose a new potential mechanism of combining a strong recent uplift and a strong water inflow in the upstream and a strong orographic precipitation on the high plateau. And we can reproduce the similar topography as we can observe here and as described here today. So if we move to the other side, to the west, in the Three Rivers region, in a local scale, our study of the thermochronological data show the different exhumation history in the Kawajibu and Baimanshishan Massif was dominated by the different uplift scenario, but they all have like a very similar Mekong River incision since 10 million years, accounting for 20 to 30% of the total exhumation. And our new data from the Kawajibu Massif showed that the Three Rivers region, the whole region, experienced a very strong Oligocene uplift, as demonstrated by the reactivation of the Lomoto Shonghu as a local thrust. And this strong uplift is responsible for the construction of the high topography, as we can observe here. So our new data also from the Kawajibu Massif help us to better constrain the tectonic evolution of the whole Southeast belt, as I have represented in the final of the first part. And we can also see like the different mechanism for similar topographic characteristics could be very different depending on the different context of the tectonic and climate, as we can see by our final Fastighate model. And this modeling also helped us to better constrain and understand the plateau growth mechanisms across the whole Southeast belt by comparing with the other models who exist already. Even though I have quite nice results, but still we still have a lot of jobs to do in the future. For example, we can have more data and dating like the argon to constrain from the Kawajibu to constrain a longer tectonic history, probably at least since the India-Asia collision. And also for the modeling part of the landscape evolution, we could involve a more realistic climatic model for better constrain the orographic effect. And we also could better explore all the hill slope processes during the landscape evolution. And it will be very interesting if we could couple in the thermochronological data with the first part into our second part. And that will give us quite nice results, I think. And I think I will stop here. And thank you all very much for